Hey, I know you're fired up to hear about the fundamental theorem of calculus part 1. It's definitely a fundamental part of the course, and I will put a video out here because this is a little tricky. You think, oh, FTC1 problems, there has to be one question they ask and one way to find that answer. There's truthfully 4 different types of questions that can be associated with an FTC1 problem. So you have to look at the information that's provided and look carefully at the question that is asked before you pull the trigger on a specific method you're going to use. Let's take a look at what we're talking about specifically. So what we want you to see, first of all, is the blueprint for the fundamental theorem of calculus. And that states that if you let little f equal big F prime of t. So the first thing I want to caution you is take a look at the little f and the big F. These notations are extremely important, that you can see that little f, when integrated, gives you big F. What on earth does that mean? Simply that if I take big F and I take its derivative, I get little f. Almost like if you take f of x and take its derivative, you get f prime. Most every textbook you look at or website will provide for you the fundamental theorem of calculus using this notation, so get used to it. When you take the integral from a to b of little f of t dt, that equals big F at b, notice the upper limit is plugged in for t, minus big F at a. The lower limit of integration is plugged in for t. This will make a whole lot more sense when we get to it. But truth be known, if you think about position, take its derivative velocity, you can think here that little f is velocity, take its integral, big F is position. So you know what we have seen in class, that little f, or velocity, is given by a v of t function, and big F, position, is often provided with notation with the letter S for position. So the other way that I want you to contemplate this is that the integral from a to b of little f of t dt equals the change in position from t equals a to t equals b. Like, for example, the change in position from time equals 1 to time equals 5 for a specific problem. The change in position. So again, if you think of big F as the position function, the change in position will be the big F function at time 5, for example, minus the big F function at time 2, for example. Let's look at some core problems so you get a better feel for what I'm talking about. So this is example 1. It reads, suppose the velocity of an object over a 2-second interval, so time is between 0 and 2, is given by the function v of t for velocity. V of t equals t squared, a simple parent function parabola. And if you guys were given this, you'd say, all right, I think I know how to deal with the graph of this. The question associated with this is, how far has the object moved in this period from 0 to 2 seconds? Well, the fundamental theorem of calculus can help us this way. We want to know how far the object has moved. We're given a velocity. The velocity is telling us in what direction and how fast it's moving, not how far the object has moved. In order to figure out how far the object has moved, we actually have to integrate velocity. In this case, integrating from 0 to 2, t squared, which is the velocity function, dt, equals, check it out now, we see when I integrate velocity, I get position. So we get the position at time 2 minus the position at time 0. So what I would do without having a lot of skills with regard to integration, what we need to do is to take this integral from 0 to 2 t squared dt and evaluate it on our calculator. So I'm taking my calculator out at this point. I'm going to my y equals screen. I put in t squared. I set up a nice viewing window and evaluate that integral from 0 to 2. This is what I got on my calculator. You've likely done the same. But I noticed that the integral of the velocity function from 0 to 2 is 2 2/3. This object has traveled a distance of 2 2/3 of 2 2/3 is my answer. Now, I don't know the distance units here. In future problems, you're going to see more specifics with regard to units. But for right now, what you need to understand is we've evaluated a velocity function from 0 to 2. When we've done so, yeah, I got the area under the curve, but in application here, what I have found is the total distance traveled in this case from 0 to 2. I'm on a mission for you to be very careful here. Do you notice some things about this velocity function? From 0 to 2, it's entirely positive. There's nothing tricky going on. I know velocities can be both positive and negative. I'm wondering what's going to go on when part of the graph is positive, part of the graph is negative. So this is what I would call a very simple problem that uses FTC1. Nothing tricky here because the velocity is entirely positive on the interval from 0 to 2. Let's keep talking. So I would write my statement here. The object has traveled 2 2/3 units. Things become a little more complicated, so don't get arrogant. Let's move. So this is problem 2. The velocity function in meters per second, now we've got a velocity unit, is given by the velocity v of t equals cosine t. Oh gosh, I know full well the cosine function is sometimes positive, sometimes negative. We're looking at the cosine function for time values between 0 and pi. The question here is asking, what is the net distance traveled? What is the distance displacement of the object? Well, in order to do this, I am going to again use my calculator to evaluate the integral from 0 to pi cosine t dt. I've got my calculator out in radian mode. I put in a window, so my x min and max is going from 0 to pi. My y min and max is going from -1 to 1. And I graph this cat and evaluate the integral from 0 to pi. Now, it doesn't surprise you to see this graph, to see this integral, which has part of its area above the x-axis and an equal portion of its area below the x-axis. So this function, if I'm traveling right and left, and positive velocity is traveling right and negative velocity is traveling left, check it out. This object is traveling right for times 0 to pi over 2, and then left for times pi over 2 to pi. And the truth is, it travels the exact same distance right as it does to the left. Can you picture this object? It's traveling to the right and then traveling back to the left. It stops where it has started. The displacement distance here is 0 meters. Now, I know it's traveled farther than that. It's traveled right and then left. It's traveled a specific distance. But the net distance, or the distance displacement here, is 0 meters. This is what I'm talking about. Be very careful with regard to what question is being asked. Here we're asked for the net distance. If this question asked for the total distance, my game would be a little different. I wonder what the next question is going to be about. Well, it's like you're Nostradamus or something predicting this. Pretty impressive. Now we're asking same exact function. This is problem number 2 continued. What is the total distance traveled of this object? Well, if I want to know the total distance traveled for the object, I don't care if it's traveling right or left. I don't want those distances to negate each other. I'm interested in the total distance traveled. So perhaps you understand this To evaluate the integral, what we want to do is take the absolute value of the cosine function. So that stuff that lived underneath the x-axis now entirely lives above the x-axis, in this case the t-axis. So when I graph this, and semi-complicated to put this on your graphing calculator, but I'm sure you've got the wherewithal to do so, I go to my y equals screen, I go math, right arrow to num, I've got the absolute value signs and put a cosine t in there, and I've already got a nice viewing window. Integrate that from 0 to pi and see what you get. Your graphing calculator picture should look something like mine. Do you notice here that the integral answer is 2? So when I interpret my answer here, I know the total distance that this object traveled was 2 meters. Was 2 meters. Just want to make quick mention here. If you looked at the bottom of your calculator screen, in this case, when we evaluated the integral from 0 to pi, we got 0. But on my calculator, I see it says negative 3.2 e to the negative 14th power. We all realize that that's taking that decimal point, 3.2, and moving that decimal point 14 units to the left. Whew, that's a number, 0.0321. That's a number we need to interpret as 0. I didn't make mention of that, so that you are all aware that when you see a calculator output like that, you need to evaluate that as 0. All right, so for this problem, we got 2 meters. Notice when they ask for the total distance traveled, you need to then take the absolute value of your function. Okay, so this time, let's put this all together. What we have is a particle travels on a number line with velocity equal to 0.3 t minus 1 times t minus 3 times t minus 5 meters per second. So this is a cubic function. I see that it's going to have zeros at positive 1, positive 3, positive 5. But the next piece of information they provide for me, which I haven't seen with the previous problems, is that s at 2 equals 7. S at 2 equals 7 meters. So they give me a velocity function. They provide for me one position value. This s at 2 equals 7 meters is suggesting that the position of the particle at time 2 is 7 meters. That's going to be important for us to answer this question. We want to find s at 5, the position of the particle at time 5. So we know the velocity of the particle. We know the position of the particle at time 7. We want to know the position of the particle at time 5. Well, all I'm going to do is write down first my integral. So I need to look at the problem and establish my limits of integration. I steal them from what's being asked. First, what's given, the position at 2 is 7, and then what is asked, the position at 5 is what I got to figure out. So that's why I'm integrating from 2 to 5. So I have to be able to steal values from the word problem. And of course I am integrating the velocity function, which is that complicated 0.3 times t minus 1 times t minus 3 times t minus 5. I know I can do that on my calculator. I'm going to evaluate the velocity function from 2 to 5. And FTC1 tells me that this is going to be equal to the position of the particle at 5 minus the position of the particle at 2. Now I call this, you guys, the strategy when you get problems like this is to figure out 2 out of 3. You essentially have 3 different components to this equation. All right? You have part 1, part 2, and part 3. And I'm here to suggest if you can figure out 2 out of 3 of those, you can use simple algebra 1 to figure out the third. So the concept here is 2 out of 3. You get a problem like this, see if you can figure out 2 out of 3. So anyway, here is the graph associated with what we're talking about. What have I done? I put in the velocity function and evaluated the integral from 2 to 5. And I get this answer, negative 0.675. You can do that calculation now, and hopefully will agree with me. So this is the integral. So underneath the integral from 2 to 5, I'm writing the value that I just found, negative 0.675. Equals. Now, S at 5. What do I put in for S at 5? Oh, that's what I'm trying to find. So I leave that cat open for business, S at 5. Minus S at 2. This is provided for me with a problem. They give me this value is 7 meters. This is what I'm talking about with regard to plugging in 2 out of 3. I was able to figure out the integral from 2 to 5, negative 0.675. I'm trying to find S at 5. They provide for me that S at 2 is equal to 7. Now you got a simple algebra 1 problem. You guys are trying to find the position at 5. I got to isolate the position at 5. What do you do to both sides of the equal sign? Yeah, add 7 to both sides. When you do so, you will get S at 5 equals 6.325 meters. So hopefully you have seen through this video some of the questions that could be asked pertaining to a definite integral type problem. The total distance traveled, the net change of position, and hey, what is the position of the particle, say at time 5? So different types of challenges that way, and we'll address some more questions that you have after getting some practice, but hopefully this video provides for you some clarity about FTC1. With FTC1, it may not surprise you, there is an FTC2 up and coming. Stay tuned. Until next time, this is Mr. Foster, Math Made Easy, Foster Films. Over and out.